Particle in a box is a useful approach to describe the nanostructures, behavior of nanostructures. And it is based on a free particle model and the presence of infinitely large barriers which restrict the wave function, hence the name, the particle in a box. So in 3 dimensions you can consider a box with the sizes like Lx, Ly, and Lz. And if we only now focus on the zero, on the x direction, on one of the dimensions, between 0 and Lx, the potential will be infinitely high. So there will be very high barriers. So this is the energy scale. And you will have V of x is 0. We will have V of x is infinity on the left and on the right. And V of x is 0 inside the wall, inside this potential. Because the potential is infinitely high, the wave function is 0 inside these barriers. So psi of x is 0 here, and it's also 0 here. And then by continuity, it also must be 0 at the boundaries here, right? So the psi of 0 equals 0, and the psi of Lx equals 0. And inside this barrier, we will have a free particle picture, particle model. That means for the one spatial coordinate, we will have this equation: h bar square over 2m psi of x double prime equals e psi of x. Within this region, restricted by these boundaries. Now we look for the solution of this equation, and then we will use the boundary conditions to find the coefficients there. Again, the solution can be in the form of the sum of the 2 exponents, or it also can be in the form of the sum of the 2 functions like sine and cosine. And I can just write a few different general expressions. Psi of x is a prime e to the ikx. I'll probably skip these indices here. It's kind of easier to write kx. We only consider one coordinate anyway. Plus b prime e to the minus ikx. Or you can write down in terms of trigonometric functions. Psi of x is then a sine of kx plus b cosine of kx, which is the same as psi of x equals c times sine of kx plus phi. You can easily show this if you remember the trig identities there. It's a straightforward way to show. But so let's use actually this last form. It's quite nice because then we can easily apply the boundary conditions to find c and phi. So psi of 0 equals 0, and psi of L equals 0. That means that from psi of 0 equals 0, we have, from psi of 0 we have this c times sine of phi must be equal 0, right? And from the psi of L, you will have c times sine of kl plus phi equals 0. So from these 2 equations, it's either c is 0 or phi is 0, right? And C0 is a boring case, so we won't consider that one. So phi must be 0. And this means our wave function is C times sine kx. Now, let's find this k, because sine of kl now must be 0 from another boundary condition. The values of k will be just this set of values, pi n over l, where n is 1, 2, 3, and so on, so integer numbers. So you can have this kn is the index there. So the solution gives you a discrete values for the for this k, which is now written here. And then you can also find the eigenvalues as a function of this number n. Sometimes this one is called the principal quantum number. Principal quantum number. And it's h bar square kn over 2m, as we know, which then can be expressed in terms of this pi n and l. You have pi square n square h pi square over 2m l square. And if we take an example for the first state there, so E1, this would be a ground state of the system, then you will have h bar square pi square h bar square pi square over 2ml squared, which is then approximately something like 0.338 electron volt per nanometer squared. You can then plug in the numbers, let's say for the width of 1 nanometer of this well, you will have the energy approximately 0.4 electron volts. So the couple of questions you can think of at this stage is what would be the range of allowed k, and what would be the range of allowed n values, right? And you need to think whether n can be 0 or not. The answer to the last one is quite easy. So if n is 0, then k of n0 would be 0. So psi of x would be 0 everywhere, right? So then your wave function would be c times sine of so psi of x when you have n equals 0 is c times sine of 0 times x, because k is 0, right? And there would be no electron in the well, so this case doesn't work. So you cannot have zero value for n here. So the energy must be non-zero then. The other question to explore is what would be the positions of the energy levels? Are they spaced equidistantly or not? And the answer to that one, it also can be easily computed. So delta E would be your energy at n plus 1 minus E of n. And that you can get quite easily, because in the n plus 1 you will have that one squared, so you will have n plus 1 squared. All other coefficients are the same, so I'm just omitting them, minus n squared, and that would all be times E1, so the first energy. Then you can open these brackets there. You will have something like n squared plus 2n plus 1 minus n squared, so those guys cancel, and the answer would be 2n plus 1 times E1. So as the n increases, the distance between the energy levels increases, so they're not equidistant. And if we then consider the energies actually for approximately 1 millimeter of the barrier, right? We have our cube of the size of 1 millimeter. Then the first energy, the ground state energy, would be something like I think it's approximately 4 10 to times 10 to minus 13 electron volt. So it's a ridiculously small value. And then the next level would be also quite close to that one, and so on. So if you decrease the size to approximately 1 micrometer, L is approximately 1 micrometer, then the E1 would be something like 0.4 micro electron volts, and so on. And you need to compare this one with the thermal energy, of course, to tell how quantum is the behavior of the system, right? So at room temperature, the KBT is approximately 25 milli-electron volts. So this is still far away from being considered like a quantum system or nanoscale system. Then if you take the size of approximately 1 nanometer, then the energy would be 0.4 electron volts, which is much bigger than KBT at room temperature. So this is a quantum system at room temperature. These larger systems, like 1 micrometer, can be quantum if you decrease the temperature to approximately 5 millikelvin, then the energies would be comparable. So for this one, KBT at 5 millikelvin, which can be reached in some of the experimental setups. Last bit to consider here is what's the value of C in the wave function. So we have psi of x equals C times sine of kx, and you can find the C from the normalization condition, right? So the wave function, the modulus square of the wave function gives you the probability to find a particle, and if you integrate this one over the entire space, we're doing in one coordinate, but it can be generalized, then you will have the integral, because it's zero everywhere outside the box. So now the integration can be just on the boundaries of the box, so from 0 to L, and then you have sine square of kn x dx. So that one must be 1. You must find the particle somewhere in there. And then taking this integral would give you C approximately, this exactly, will give you C equals square root of 2 over L. I'll leave you to compute the integral. So psi n of x now is then square root of 2 over L sine of n pi x over L, now in terms of the principal quantum number and the size of the well. And that's the general result for the particle in the box in one dimension. And we can then generalize it to 3 dimensions. So in the case of 3-dimensional situation, you can write down the wave function. Now it will have like 3 principal quantum numbers, nx and y and z, x, y, and z coordinates, and because those are all independent, you can put the same coefficient here, so it's 2 times 2 times 2 from each coordinate. You have lx, ly, lz times the sine of pi nx x over lx sine of pi ny y over ly, and then sine pi nz z over oz. The total energy is also a function of these 3 quantum numbers. Will be pi square h bar square over 2m times the sum of these guys plus ny square ly square plus nz square over oz square. And yeah, you can then write down for the ground state, you will have all these principal quantum numbers equal 1. So E111 state is the ground state, and you will have pi square h bar square over 2m 1 over Lx squared plus 1 over Ly squared plus 1 over Lz squared. And that's basically it. How can we use this this general description? We can do the following. So in the three-dimensional case, all these Lx, Ly, and Lz, they are macroscopic. They're macroscopic. In a two-dimensional case, one of the dimensions will be nanoscale. One dimension is in nanoscale. In 1D, there will be two dimensions in nanoscale. And in 0D, all three dimensions are nano-sized.